I want to do some examples where we convert rectangular coordinates to polar coordinates. So let me put the instructions here. And as we know, polar coordinates, there can be many different representations because polar coordinates use an angle theta, and we know that theta could be any coterminal angle. So the typical way that you would do this, and if you chose to do it a certain way, you would follow this probably. So convert the rectangular coordinates to polar coordinates where the r value is positive and the theta value is between 0 and 2 pi, meaning it's a positive angle because theta is greater than or equal to 0, and it's within the first revolution of the coordinate plane to 2 pi. So it's very natural to choose your angle to be within the first revolution of the coordinate plane rather than multiple rotations. It's also natural to choose your theta value to be positive and not rotate in the negative direction. And then your r value, you typically want to be positive because if you recall, if r is negative, you actually move in the opposite direction of your angle that you have. Okay, so we're going to follow these guidelines here. Okay, so let's look at example 1. So I need to give you some rectangular coordinates, and then we're going to convert those to polar coordinates. Okay, so let's look at, how about 3, sorry, I need parentheses, 3 square roots of 3, comma, negative 3. So those are the rectangular coordinates that we want to convert to polar. Okay, so what I'm going to do is I always, lots of books and things present formulas for doing this. And really, if you can visualize something and actually solve a problem, as opposed to regurgitating a formula that you're looking at currently or that you think you remember, if you can actually solve a problem, if you can write it out and work it, there's so much more value to that. So that's the approach I'm going to take. Now, since these are rectangular coordinates, I know this is x and this is y, meaning that I need to move right 3 square roots of 3 and down 3. Okay, so this distance here is 3 square roots of 3, and this distance here is negative 3. So this is my point. And what I want is to convert those to rectangular coordinates, meaning I need to know, so all my rectangular work will be in red, I need to know my rotation from 0, meaning from the positive x-axis, to the axis on which my point lives, which is right here. I need to know this theta value. And I need to know the length, how far I'm going to walk from my origin to this point. So I need to know this distance, which is what we call r, okay? So I can work on those however I like in whatever order that I want. Let's start with theta, okay? And so when I look at theta, what I want to consider is that by creating this r and using my x and using my y, I've got a right triangle. So what I'll do is I'll redraw that triangle over here, approximately. I know this is 3 square roots of 3. I know this is negative 3, these distances. And if I want to know theta, it would be useful to first find my reference angle, theta bar, right here. Well, theta bar, my reference angle, since I know my opposite side and my adjacent side, I can use the inverse tangent function. Remember, inverse tangent will output an angle if I input the correct ratio to it. So the ratio that I will input is opposite over adjacent because this is tan inverse. So opposite, negative 3, adjacent, 3 square roots of 3. Now, when you're doing a reference angle, let me make a note of this. When calculating a reference angle, always use a positive ratio, okay? Reference triangles can live in any quadrant. It doesn't matter positives and negatives. So reference angles always use positive numbers because this is just a right triangle. And if you take this right triangle out of context, it doesn't matter that this is negative 3. So I need opposite positive 3 over adjacent 3 square roots of 3. If you put that into your calculator, um, if you have one of the calculators that I like to use, a Casio FX 115 ES Plus, there's some Texas Instruments as well. It will output the proper radian measure the way you want it. But most calculators you need to be in degree mode here and then look at the radian measure. So if you're in degree mode, your calculator is going to give you a 30-degree reference angle, or we're going to go with radians because polar coordinates are typically using radians. So pi over 6 is our reference angle right here. So what does that mean that theta is? Well, theta is not quite a full rotation of the plane, right? It's like rotating 2 pi, but you need to take away this little bit here. So theta is going to be 2 pi, take away the pi over 6. It's just short of 2 pi. And if you take 2 pi minus pi over 6, well, that's the same thing as 12 pi over 6 minus 1 pi over 6, which is 11 pi over 6. So the theta that we'll use in our polar coordinates is 11 pi over 6. And 11 pi over 6 is greater than or equal to 0 and less than 2 pi. It rotates in the positive direction, and it's less than a full rotation. So it satisfies the criteria we have here. So we have our theta. Now we need our r, and r is the hypotenuse of this triangle. Well, that's pretty simple because r can be calculated using the Pythagorean theorem. So I can say that r, or r squared, if I will, because this is r squared equals 3 square roots of 3 squared plus 3 squared. So r squared equals, let's see, if you multiply 9 times 3, you get 27, plus 3 squared is 9. So r squared is 36, meaning that r, take the square root, r is 6. So this rectangular ordered pair equals this polar ordered pair, r comma theta, so 6 comma 11 pi over 6. Okay, and this is r and theta now. So here are the polar coordinates for that set of rectangular coordinates. And if you plot this point, you will see that you will land right here, the same point as if you plotted this rectangular point. Let's try one more. Okay, let's do the same thing again. We're following the same instructions. Convert these rectangular coordinates, this x and y values, to polar coordinates. And so again, I'm not going to just straight apply formulas. I'm going to actually solve the problem. I'm going to look at what this is saying. So x is -1, so I go left 1 unit and I go up 2 units. So this distance here is -1 and this distance here is 2. And it can be useful to think of this like this. And now what I want is r and theta. So I need to determine my theta value and my r value, which is the length of this hypotenuse. So let's go over here and work on our right triangle that we have in this picture. So we know this is -1, we know this is 2. If I want to know my theta value, then I need to know my reference angle right here, which is theta bar. Theta bar, again, is going to be, I know opposite and adjacent, so I'll use tan inverse of opposite 2 over adjacent +1. Remember, use positive ratios when determining reference angles. And if you calculate tan inverse of 2 in your calculator, you get kind of a crazy angle measure, like 63.4 degrees. Now, we would have to round that. So instead of rounding, we're going to call the reference angle, we're just going to leave it as tan inverse of 2. Well, that's interesting then. What would theta be? If this is our reference angle, theta bar, then what's theta? Well, theta is a rotation that almost gets over here to pi. It comes up this much short though. So theta will be pi minus, because you have to take away from pi to get back here, minus what? Well, this is theta bar. So theta will be pi minus theta bar. In other words, theta bar in this case is tan inverse of 2. So theta will equal pi minus tan inverse of 2 if you have to be precise. So that's our theta value, okay? If you want to approximate that, make sure your calculator is in radians mode and type pi minus tan inverse of 2. And if you approximate this, you get approximately 2.03 rads. Okay, so this is exact, this is approximate. So different scenarios could call for different things, but we know how to do both. Okay, so we have our theta value. Now we need our r value. R is going to be the hypotenuse of this triangle. So r squared equals 2 squared plus 1 squared. So r squared is 4 plus 1 is 5. So r is the square root of 5. Okay, so this rectangular ordered pair equals the polar ordered pair r comma theta. So r is square root of 5. And theta is exactly pi minus tan inverse of 2. So this is the exact polar coordinates. If you want to approximate, well, you could calculate the square root of 5 approximately, and you'd get r to be approximately 2. Let's say 24, comma theta, which we already said is approximately 2.03. So this would be r, and this would be theta. And you could have theta in degrees if you want to. Just make sure you have the degree symbol. But either one of these is perfectly fine depending on the instructions. You don't round unless you're told to round. Unless the instructions specify, okay? If you think about if you're on a job as an engineer and someone gives you measurements that are already rounded for you, say they rounded too much. You know, a bridge is they tell you the bridge is supposed to be 200 feet long, and you build it, and it's 3 feet short because they rounded it from 203.4 all the way down to 200. So it's better to be more precise in your answers unless you're told otherwise, okay? So the exact answer is better than the approximate answer because you're taking away some precision by rounding.